I want to introduce, well, thank you for coming today. I know it's a couple hours, is a lot out of your day, but I know you're going to get a lot out of it. This is Eugene.
Hi.
Ngai. I met him about a year and a half ago. He owns a company called Chemically Speaking, Incorporated. And I went to a class of his up at Irvine and was so impressed, I thought, well, I've got to get him down here so that I can not only have him give EH&S training, but the whole campus, because he has a wealth of knowledge, 40 years of study of compressed gases. So, Eugene, thank you for coming, and enjoy the show, folks.
Thank you. Thanks. Morning. I'm happy to be here. It's been an interesting week so far. What today will be is a brief overview on compressed gases. I teach a 3-day class where we look at quite a bit of the properties of compressed gases, emergency response, containment, etc. But what I want to do today is just introduce you to compressed gases. You have quite a variety of gases on campus with a whole variety of hazards. We'll talk about those. I spent 4 hours yesterday with your emergency response team on site. We talked about emergency response procedures, gas detection. I brought along a case of show and tell. This afternoon, I'm going to have a second class in which we can talk in more detail about a whole variety of topics. I leave it up to the audience. How many people plan to attend the second session? Okay, good. We can talk more about metal hydride gases. We can talk about cryogenic liquids. We can talk about cylinders and valves. We can talk about emergency response. We could talk about pretty much anything you want to regarding compressed gases. I have about 20 gigabyte of data. We'll talk about a lot of that stuff in the next few hours, okay? I'll give you a brief introduction on myself. I started as a young engineer. I'm a Chem E by training, master's in environmental engineering. But I started with a company making arsine, phosphine, and silane, some very friendly gases, back in 1972. And I pretty much spent 40 years in the compressed gas industry. I was vice president of a company that I built from a small company into a worldwide operation making MOCVD gases, arsine, phosphine, hydrogen selenide, silicon tetrafluoride. In fact, one of the products that I'm very proud of that we developed was a product called blue ammonia. You know, many of you probably, what's he talking about, blue ammonia? It was essentially ammonia that gave the researchers the ability to grow gallium nitride. Up until the mid-1990s, it was very difficult to grow gallium nitride with any good efficiency. Blue ammonia was a product with purity that allowed them to do that. Now, today, they're selling it called white ammonia today. Hydrogen selenide is another product that I've been playing around with pretty much 40 years. So what I want to give to you is background and learnings I've had in the last 40 years. After Air Products bought the company I was with, they didn't really know what to do with me. So I spent 11 years traveling the world, playing around with many, many compounds. I wanted to understand behavior. I wanted to see what would happen if these products were released and what we could possibly do in order to put the genie back into the bottle. Chlorine trifluoride is probably one of the most reactive chemicals I've played around with. This is an example of chlorine trifluoride. We dripped it on a piece of chicken to see what would happen if it contacted human flesh. And here you'll see it's reacting with the oil. Diborane, I consult for a specialty chemicals company called Voltaics. They make a lot of designer chemicals, germane, disilane, trimethylamine, trimethyl boron. These are some of the new compounds that are being used within the semiconductor industry. Trimethyl aluminum, I tried to burn down a gas cabinet in Holland about 8 years ago to see what can happen if all of a sudden I released a lot of trimethyl aluminum in a gas cabinet. One of my champion clauses is silane. How many people are familiar with silane? Okay. Silane is a pyrophoric gas, and many people have been injured as a result of silane releases over the last 40 years. I'm doing a silane class tomorrow where we'll talk a lot about silane. But one of the challenges we have within the industry is, as these packages get bigger and bigger, how do we safely use these materials? I was test director for silane release testing in New Mexico, 2011, 2012. It was a $500,000 study. We spent a week and a half out in the desert releasing silane in some fairly significant quantities. One of the questions that was asked by the fire code was, what would happen if I have a silane cylinder here and I released silane, would we rupture the cylinder? And we did 3 tests. These are 40-foot flames. We had a SiO2 cloud that was about 450 feet. We did a lot of testing on silane in order to rewrite G13, which is the CGA standard that regulates silane activities. This is essentially one of the tests. And there you see, we dump 150 kilograms of silane in 2 minutes. That's essentially what the code requires, that we release that silane in that amount of time. We never did burst that cylinder next to it, despite the intensity of the flames you see here. I'm a consultant now. I spend a lot of time on standards activities and a lot of mentoring today. I truly believe that I need to pass on to this generation the learnings from the last 40 years. Especially with the compressed gases, there have been a number of incidents in the 60s and 70s that many people are not even aware of, with many of the gases that you folks are using today. So I sit on a number of standards committees. The one that you should be familiar with is 10298, toxicity. That is the world standard for toxicity. It's very, very important today because of GHS. How many people are familiar with GHS? Okay. If you're not, you will be in the future. That's Global Harmonized System. What they're trying to do today is internationalize standards for worker safety information and transportation. And U.S. has committed to rewrite the OSHA standard and transportation standards to the GHS standards. Flammability is 10156. But as well, I sit on NFPA 55, which is compressed gases, 400 hazardous materials, and 318, which is semiconductor. I have a number of customers. I'm not going to bore you with the details on that. I think the more important thing is, one of my part-time activities is I spent 25 years teaching safety and emergency response around the world. This was an incident occurred in New York City. A sarin cylinder was found. And at that point, New York City Fire didn't have a way of getting that cylinder out of the apartment building. That's when they realized that they needed what we call a cylinder containment vessels. These are ASME vessels that are designed to overpack a leaking cylinder. I designed these in 1988 for emergency response use. There are probably about 350 of these worldwide that are used for emergency response purposes for compressed gases. We're not going to talk about emergency response. I just wanted to make you aware of some of these activities. Yesterday, we spent some time with the emergency response team talking about pre-plan. How do you respond to a cylinder incident? How do you respond to a worst case event? It's what we call pre-planning. This is an example of a pre-plan. When I was in New York City, in 1998, one of the firefighters said, you know, my worst nightmare is someone taking a propane cylinder and filling it with WMD, putting it down a subway platform. I have mass chaos. How do I deal with it? I can't get equipment down 40 feet into the ground. we developed essentially a 20-pound propane capping kit. This is a kit that now they can use for a specific purpose. And over the years, I've designed quite a variety of compressed gas emergency response tools. I do a lot of training around the world, especially fire departments. A lot of firefighters. Yesterday, you guys invited the San Diego County hazmat for the training. I just did a class up at in Hayward for the Northern California fire prevention officers, and a lot of universities. I do a lot of nano fabs. UPenn, Harvard, the new graduate school in Saudi Arabia, and then a lot of gas suppliers. What you saw in that video was what I call field of heat training. I consult for 2 silane manufacturers in the US, REC Silicon and Dow Corning. One of the trainings I do is I want people to feel the heat, to actually experience what we call a popper. How many people have experienced something like this? When I first started in industry, 50% of the silane cylinders that I had were poppers. That's because valve technology was not that good back in the 1970s. And I used to be scared, more scared of silane cylinders than I was of arsine or phosphine. And we'll talk a lot about silane safety tomorrow. Now, what I want you to do is ask questions. I'm not going to be able to give you all of the details on all of the gases you might have an interest in. I would encourage you to take my email address down and email me questions. I have people that have emailed me questions over the last 40 years. I continue to mentor some engineers. I've been mentoring an engineer in Taiwan for the last 15 years. So let's start with our presentation. Essentially, what we're going to do is we're going to talk about chemical and physical properties. What are some of the hazards? Package. What types of cylinders are used? How are they made? Valves, outlet connection, handling and storage. Where should I store these cylinders? And use. What are the key elements of a compressed gas safety program? Well, one of the key requirements is knowledge, and that's essentially what this class is about. This is being recorded so you guys can use it in the future. But what's the other thing? Knowing symptoms of exposure. If I'm using this gas, how do I know I got exposed to it? Gas detection for some of the toxics is an absolute requirement because being able to sense or detect a high level is very difficult for many gases. PPE, what should I be wearing? I think you have an excellent chemical safety program here. I reviewed it. I'm going to be meeting with the committee tomorrow. I just have some minor additions to the program in order to expand it to other uses. For example, how many people are familiar with what this is? This is new technology. This is a hydrogen cylinder. This has 13 liters of hydrogen in it. This is on a metal hydride solid, which adsorbs the hydrogen. This should have 2,000 psi of pressure, but in reality, it's probably less than 30 because of the metal hydride. When I screw this in, this will start to purge. You hear that purging? It's purging the fuel cell. Once it's finished purging, the fuel cell will take the hydrogen, combine it with the oxygen in the air, and essentially generate 2 watts of electric. And here This is essentially running off of my fuel cell. I charge my iPhone with this. This will give me 8 charges on my iPhone rather than using a battery. This is essentially new technology that you're going to see in the future with hydrogen, right? This is the new hydrogen-based technology that you're going to see more and more of. Now, they believe that consumers like yourself will be using these types of cylinders in the future. BIC just bought a company that makes this product because they truly believe that every drugstore and every 7-Eleven will have these little hydrogen cells that you can use for generating electric, okay? You're going to see more of this here on campus because there's going to be more and more research on materials like this. Now, there is not a policy today regulating this material, right? Gas generators. They have fluorine generators, arsine generators. Those are all being used today in laboratories, and how do you regulate the use, okay? You have many compressed gases used on campus, but I think the important thing is you have some very formal guidelines that direct you on their usage, storage, and handling. These are some of the guidelines, and I don't know how many people are familiar. I know there are some folks from other campuses here, but these are the San Diego guidelines. I reviewed all of these, and we'll be making some comments tomorrow. So, what's a compressed gas? It's really a chemical with the added hazard of pressure, right? It could be toxic, it can be corrosive, it could be flammable, but more importantly, it also has a physical hazard, which is pressure. In some cases, it could be very cold. Liquid nitrogen. Many folks use liquid nitrogen, and liquid nitrogen is a fairly cold material, minus 196 degrees C. Many, many different hazards. There are over 200 gases packaged in cylinders today. But not only is it gases that are in cylinders, there are many liquids that are put into cylinders because people want to dispense them in a closed system. So they'll put a liquid into a cylinder and pressurize it, and you'll bring it out through a dip tube into your reactor or into your system. Many, many gas mixtures, as long as it's safe to do so, will make the mixture. There are certain safety rules that we follow, but it can vary anywhere from parts per billion. And you have an environmental lab here that does a lot of environmental chemistry. They're probably looking at ppb concentrations, very accurate mixtures that are required to monitor environmental conditions. So, what do you need to know? Gases come in 2 physical states. One is essentially what I consider to be a compressed gas. It's essentially a chemical that has a critical temperature that's less than ambient. And as a result, it can no longer exist as a liquid or a solid because your temperature is already above the critical temperature of the material. No matter how much pressure you put on it, it will remain a compressed gas. So the way you can tell how much is in a cylinder is by using a pressure gauge, right? Hydrogen, nitrogen, argon are all compressed gases. The other form is liquefied gases. Critical temperature above ambient. And what happens? As you pressurize it, you reach the vapor pressure of that material at that temperature, and it will start to liquefy. If you were to pick up the cylinder, you would actually see liquid inside the cylinder. How many people have propane grill here? Anyone have propane grill? All right. And how do you know how much is in a propane cylinder?
By the weight.
What's that?
By the weight and feeling it.
Yeah. That's why a pressure gauge will not tell you how much is in there, because as long as you have liquid propane, it's going to stay the same pressure, right? The only true way of telling is by weighing that cylinder. You put it on a bathroom scale or whatever in order to weigh that cylinder. And what else do? You subtract the tare weight. If you look at your propane cylinder, you'll see it say TW. TW is the tare weight of that cylinder, and that's the cylinder empty. And so the combined weight is the total weight. And so you subtract the tare weight, and that tells you how much is in there. The key for liquefied gas is that the pressure varies with temperature. And there are many liquefied gases that have very low pressure. Chlorine trifluoride, boron trichloride are very low, less than 10 psi in pressure. HF is another one. It's less than 1 psi of pressure at ambient temperatures, at 21 degrees C. How many people use acetylene here? And when you look at acetylene, this is an acetylene gauge, right? It's the only pressure gauge that has a red zone. Why is that? Acetylene, which is C2H2, is very unstable. Acetylene wants to decompose. In fact, the decomposition energy is higher than oxidation. And once acetylene starts to decompose, what happens? It starts to accelerate through the entire mass until all of it is consumed. Now, the safety rule in the United States is you don't use acetylene above 15 psi, and that's why you have the red zone. Because that pressure is higher than that, you can wind up with a decomposition reaction that can destroy your system. So how do you get acetylene? Because shipping acetylene at 15 psi, you're not getting a lot of material. So how do you safely do that? Acetylene is the only gas that is shipped in a cylinder that is filled with a solid. This is a solid material, and what happens? They actually fill this with acetone, or DMMF, another solvent, and they actually dissolve the acetylene in the acetone. The reason for this is this acts as a flash arrestor. If someone accidentally torches the cylinder, and plumbers do that quite a bit, they turn around, they light the torch, and they turn around, they look at something, sometimes the torch will hit the side of the cylinder. They can initiate the decomposition reaction. What this does is it is a flash arrestor. It'll absorb that decomposition energy and quench the flame. Now, if the cylinder is damaged, you no longer have the ability to quench flame. And now how can you damage it? If you drop the cylinder, you wind up cracking the solid material, you now have a cavity in which that can happen, okay? So just remember, acetylene cylinders are filled with a solid. How many environmental folks are here? Okay, acetylene cylinders in a fire could explode. And the one takeaway that you should know is that up until recently, the best material that was used for acetylene was asbestos. So assume that you have asbestos contamination when you have an acetylene cylinder explode. Now, yesterday, we talked about special rules for the emergency response team in the event of a fire around an acetylene cylinder. There's some unique things that, or unique instructions that we have for the ER team, because this represents a unique hazard. You're welcome during the lunch break to come up and take a look at any of this stuff. I hate this. Yeah, we talked about this yesterday. Acetylene cylinders have some very unique hazards in a fire. The decomposition reaction in some rare cases can continue. Acetylene cylinders have been known to rupture in some rare cases up to 24 hours after a fire has been extinguished. And a lot of firefighters are very concerned about that because it killed one firefighter in London about 15 years ago. And as a result, in Europe, if there's a fire around an acetylene cylinder, they will evacuate the area for 200 meters around that cylinder for 24 hours. Now, the Europeans have done a lot of testing as a result of that. Now they've stepped back on that rule. And yesterday we talked about, and Doug will remember my conversation about probies. We will actually have a probie go up and feel the sides of a cylinder to see whether there's a hot spot. If there's a hot spot, that indicates that there's a decomposition reaction going on in that cylinder. And then there are special procedures on how to cool that cylinder to prevent that reaction or stop that reaction. So let's talk about hazards. Hazard is the ability to injure or damage. There are both physical and chemical hazards. Almost all gases are hazardous materials, simply because of the pressure hazard. What many people forget is that many chemicals have multiple hazards. When you're dealing with a material like arsine, it's a highly toxic gas, but people forget that it's also a flammable gas, right? Phosphine, highly toxic, but it's also a pyrophoric gas. So you need to be aware that there are what we call subsidiary hazards that you need to be aware of. Physical hazard is pressure. Pressure can injure you, and under the regulations, any gas, even compressed air, with a pressure greater than 25 psig is classified as a hazardous material. Cryogenic liquids, very cold. These are compressed gases that are liquefied by cooling it down to their boiling point. As you can see, you have some fairly cold temperatures here. You don't use liquid hydrogen here, but at some point in your career you might. And what's the danger with liquid hydrogen? One of the dangers with liquid hydrogen is you can liquefy the surrounding air on the piping. And as a result, you wind up with liquid air around the piping. If you use liquid helium doors are very unique in design because what can happen? Liquid helium could actually freeze the air and plug the liquid door. So there's special doors that are used for helium that are very different than a liquid nitrogen door. There's very special procedures on how to get the dip tube into that container. What's the other thing you should be aware of? Well, each liter of these liquids can expand to a lot of gas. For example, nitrogen. 1 liter of nitrogen will rapidly expand into about 700 liters of gas. So you can have an asphyxiating environment very quickly if you have a cryogenic spill.
Eugene,
Yes?
wasn't there an incident a few years ago in Texas regarding liquid nitrogen?
Yes, I'm glad you reminded me. There was a professor that didn't want to lose his liquid nitrogen in his door, so for whatever reason he decided to put a plug on the pressure relief device on his door. And fortunately, the door ruptured in the middle of the night and it blew right through the concrete floor into a lab above him. It did about $200,000 worth of damage. But that was an example. When you have liquid, a cryogenic liquid, in order to maintain the cold temperature, it has to vent a certain amount of vapor every day if you're not using any of that material. So if you're using liquid nitrogen, you need to be aware of that particular hazard. Thanks. What else? Metal embrittlement. You, as the user, need to have proper PPE. All of us have probably taken something out of the freezer at some point and our hand stuck to that package, right? But your hand then warmed up and the ice melted and you could release your fingers. Well, if you do the same thing on a liquid nitrogen pipe, you're not going to get your hand off. Okay? They're going to have to tear your flesh in order to get that off. So you need to be aware of proper PPE. Asphyxiation hazard. One of the other things that you should be aware of is that the colder a gas gets, the heavier it is. Now, yesterday I talked about an example, a very tragic incident. A user was running out of liquid nitrogen in the Northeast during a blizzard. Called the gas supplier. The driver pulled in. The facility dug out the snow around the tank. They piled the snow around the tank. The driver hooked up his hose and started to fill the liquid nitrogen tank. What he didn't realize was that there was a valve that was open on the backside of the tank. Since the liquid nitrogen was coming out and it was cold, what happened? It settled in the pit that they dug around that tank, even though it was open. And they found the driver 30 minutes later dead. He died of asphyxiation. Now, you and I would argue, wait a minute, that was open air. How can that be? Well, when you have a material that's very cold, it will settle, right? It'll go into a low-lying area. And since it continued to pour out, he wound up being asphyxiated. Very, very tragic incident. I did an audit of a government facility in which the researcher was 40 feet below ground. It was in an isolated laboratory. They didn't want any disturbance from any environmental conditions. But the challenge they had was he was down there using a lot of liquid helium for his devices. Now, how do we make sure we check on this guy to make sure he's not asphyxiated, right? Chemical hazards are toxicity, reactivity, corrosivity. And when we talk about gases, the primary route of entry is inhalation, breathing the gas, right? That's why respiratory protection is critical when you're handling many of these toxic gases. Now, what are the safeguards that you have here? Well, the requirement to be in a very well ventilated area. And one of the things that Doug and I talked about is, well, if that's your primary safeguard, how do you know that the ventilation is always on, right? The second one is gas detection. That will indicate that you have a high level of the material. Dermal route of entry, through your skin. Not many gases have a dermal route of entry. Hydrogen cyanide, cyanogen chloride are some of them. Many gases, however, will react with the moisture in the air and become a corrosive material. HCl, chlorine, ammonia, and it'll deposit on the moisture on your skin and it becomes an irritant, okay? Now, as I indicated to emergency responders yesterday, a straight gas release, you might not have a dermal hazard. It can change, however, based on the conditions of the release. For example, if I have arsine and it's on fire, it becomes arsenic trioxide. Now it becomes a dermal exposure issue. Diborane is B2H6. It's thermally unstable. It wants to become decaborane. And in that cylinder, it continues to decompose into the higher boron compounds. Now, why is that important? Pentaborane is a severe dermal toxin. We had an incident in which a guy was cleaning a cylinder, a pentaborane, or actually it was a diborane cylinder, and what was the mistake he made? He didn't remove his gloves properly. when you use PPE, you should also know how to properly put it on and take it off. And what happened was he wound up touching the outside of his glove that was contaminated with pentaborane. Now, what are the symptoms of pentaborane poisoning? Temporary paralysis. He was temporarily paralyzed for 24 hours. Now, you can imagine what goes through your mind when you're temporarily paralyzed, okay? That's from touching the pentaborane. Now, where can you find that pentaborane? If you use diborane, diborane will decompose in your system to the higher boron compounds. And it will start to plug your regulator, it'll start to plug your mass flow controller, and at some point you need to take it apart and clean it. That's where you're going to get the exposure, okay? You just need to be aware that that condition can exist. Ingestion. Not very many people will swallow the gas. So, what's a TLV or a PEL? You all have gone through safety classes, right? What does that mean? If I said, hey, Doug, I want you to sit here, the PEL for arsine is 50 ppb, and I want you to sit here for the next hour and inhale this. Is he going to be okay? I think we talk about a lot of values. The safety group will talk about many, many different values, and I think what you need to know is what does it really mean? A TLV or a PEL is a worker safety level. It's a level which you could be exposed to for 8 hours a day for your 30-year work career and not have an ill effect. That's essentially what the meaning of a TLV was, okay? So, in many cases, you are monitoring at some level of the PEL or the TLV for your toxic gas. So just because the alarm goes off doesn't mean that you instantly need medical attention. You have a problem in your system that you need to take care of, but that's what the meaning of TLV or PEL. Now, TLV is a recommended value. Threshold limit value is by the ACGIH. PEL is the OSHA level, which is the mandatory. So this is recommended, and typically this is much more conservative than PEL. So with that in mind, what did I say? Arsine is 50 ppb, right? PEL. I'm going to give Doug $100. He's going to sit there and breathe this 100 ppm arsine mixture, right? How many people think that he'll be okay? Is 100 ppm arsine mixture a toxic gas under the regulations? How do you know? How do you classify when you deliberately take a toxic material and you dilute it with a non-toxic compound? At what level does it no longer become toxic? So, how many people say this is a toxic mixture? Okay. Okay, how many people work with acetylene? Acetylene. How many people have smelled acetylene? Acetylene has a very unique odor, right? What's the odor smell like?
It's kind of sour almost.
Okay. Okay. Very pure acetylene has no odor. What you're smelling is phosphine. Arsine and phosphine impurities in acetylene grade C can be up to 500 ppm. It all comes from the calcium carbide that they use to make the acetylene. And typically, many acetylene plants will have a solid material which they call monkey dust. I don't know why they call it monkey dust. And it actually reduces the amount of arsine and phosphine to the 500 ppm level. So in reality, what you're smelling is phosphine. Okay? Now, you've been exposed to it when you smelled it. But did you get phosphine poisoning? No. Did you get arsine poisoning? No. People get exposed to acetylene every day, plumbers on a very frequent basis. And typically, the arsine and phosphine can vary up to 500 ppm. So what level of arsine is not a toxic gas under the regulations? It's 4,000 ppm under the regulations. So you could buy a 1,000 ppm mixture of arsine and it could be labeled as a flammable or non-flammable gas, okay? And here you'll see acetylene. Do you think acetylene should be labeled a toxic gas? I think therein lies the dilemma. When you have a material that you're used to with a toxic gas in it, it can never be toxic because you're used to this material. But yet, if you deliberately take a toxic material and mix it, most people can't accept that any concentration cannot be toxic, right? The key is dose. Too much of anything will kill you, right? Too much oxygen will kill you. You can't breathe pure oxygen for an extended period of time because your body will go into shock and you'll die from oxygen poisoning. Now, how do we label a material toxic? It's based on what we call the LC50 value, lethal concentration 50%. And what this is for gases, we expose 10 white albino rats to a concentration of the gas, and then we observe the population for 14 days, and if half the population dies, that's my LC50 value. GHS, or the Global Harmonized System, uses a 4-hour exposure rather than a 1 hour, and that's essentially 50% of a 1 hour exposure. So you'll see LC50 values being used for toxicity classification, both in transportation and in worker safety. Now, that doesn't address chronic exposure. This is more acute, right? We're looking at acute exposures here. And what do I mean by acute? Acute is single exposure, high level. Chronic is low level for some extended period of time. That's your carcinogens and mutagens that you're worried about. Now, an LC50 value of less than 5,000 ppm means it's a toxic gas under the transportation regulations. If it's less than 200 ppm, it's highly toxic. Now, within your system, your hazard classes are based on LC50 values, right? You have a hazard class 1, 2, 3, and 4. And it's all based on LC50s. Transportation in the US, they divide it into 4 zones, A, B, C, and D, and that's so that they can use additional requirements for the package because of the hazard. It's similar to your system here, where it's separating the materials into different hazard classes so that there are additional requirements as the toxicity increases. 10298 is the reference standard internationally for LC50 values. These have been reviewed by toxicologists both from the US and from Europe. It was just updated in 2008. What else should you know? There's a difference between the OSHA and DOT on classification of the toxicity. OSHA considers anything below 2,000 ppm as toxic. Anything above 2,000 to 5,000 is typically corrosive. Now, what would that affect? Hydrogen chloride, for example, is about 3,100 ppm LC50. So under the worker safety regulations, it's a corrosive gas. It's not a toxic. Ammonia, same thing. It's a corrosive gas rather than a toxic gas. You just need to know the differences between that. We talked about acute and chronic Now, what's the symptoms of arsine poisoning? Anyone use arsine here? Okay. What's the symptoms of arsine poisoning? When you use a gas, you should be familiar with the symptoms because there's nothing worse than being afraid of being exposed, right? Oh my God, did I get exposed? This happened at a university last year. It was an undergraduate chemistry class. They were doing an experiment that went wrong. The reactor broke, and one of the students thought he smelled garlic. And you know, when you have a group of students together and they start talking, one thing led to another, and all of a sudden they said, oh my God, did we get exposed to arsine? All of a sudden, this chemistry experiment became a massive response. They wound up transporting 97 students to the hospital for arsine exposure. What's the treatment for arsine exposure? Whole blood transfusion. That's the only medical treatment for arsine poisoning. Think about trying to do whole blood transfusion for 97 people. You can imagine the chaos. Essentially, this was a non-event. This was an event that just built from a little thing into a significant event which involved thousands of people. They had 100 firefighters respond. You can imagine how many ambulances it took to transport 97 people. They actually commandeered buses in order to transport these students because others were afraid that they had contaminated victims. They didn't want to become contaminated themselves, okay? So, my suggestion to you is when you're using these highly toxic materials, know what the symptoms are, and more importantly, gas detection is absolutely critical when you're using these. How many people know what arsine smells like? I have smelled arsine throughout my career at very low concentrations. I could smell it at about 5 ppb. It's not unpleasant. Many people say it smells like garlic. Yes, at certain concentrations it smells like garlic. But at other concentrations it smells like if you've taken a steel wool pad and cleaned a pan with it, you get that metallic odor. Sometimes arsine will smell like that. Okay, it depends on the concentration. But it's not unpleasant, and that's why people get overexposed. It's not like HCl, which is an irritant, or ammonia, which is an irritant. What's phosphine? What's the symptoms of phosphine exposure? It's respiratory. You get pulmonary edema. What happens there is your lungs start to get irritated, and what happens? In response, your body starts to secrete fluid, and your lungs fill up with fluid, and you die. You drown, essentially. The medical treatment for phosphine poisoning is supportive. They actually drain your lungs and give you oxygen, and your body repairs itself. So you just need to be aware of the symptoms. You folks use, I think there's a user here on campus that uses NO, nitric oxide. What's the symptoms of nitric oxide poisoning? Nitric oxide has delayed pulmonary edema. It means that you can be exposed to high concentration of nitric oxide, not be aware of it until hours later. All of a sudden, your lungs start to fill up with fluid because of the delayed response. If you remember the space shuttle explosion a number of years ago, the government said, hey, don't approach any of the debris because you could be exposed to a material that will give you delayed pulmonary edema. That was because they used NO2 as part of their propellant system. And they were worried that people were going to be exposed to NO2 and wind up with an ill effect. So, medical protocols are absolutely critical. Know what the symptoms are, know how to treat. Now, these are written by the U.S. Health Department, and here on campus, you guys are tied into all of these medical protocols. Just be aware that these are available. Take a look at them. Yes, sir?
So what are the symptoms of arsine?
I'm sorry, what?
What are the symptoms of the toxin that you were talking about, the exposure that the kids got?
The most obvious clue is when you urinate, your urine will be red. Essentially what's happening is arsine will destroy your red blood cells. And what happens then is your body is trying to eliminate the dead blood cells, and your urine becomes red as a result. Now, you won't die from that. What you will die from is kidney failure, because your kidneys get overwhelmed by the dead blood. Now, if you get proper treatment, you'll recover. There was a case called the Asia freighter incident a number of years ago where about 8 sailors got exposed to arsine. They got very severe exposure. 3 of them suffered renal failure, which is their kidneys failed for about 6 months. And they recovered because of the proper treatment. So as long as you get treated, you're going to be okay. I think mentally, you may not be, but physically, you'll recover, okay? I think just be aware that these exist. You guys have them on your website. Just take a look at it. If you're going to use any of these materials, you should be aware of the medical symptoms. Toxic metal hydride. This afternoon, we're going to talk a lot about arsine, phosphine, and many of those other materials. What are these? These are essentially the metals which have been reduced. Hydrogen selenide, arsine, phosphine. Now, what are the general characteristics? Almost all are toxic with the exception of silane. Right? Silane is the only metal hydride that is not toxic. In fact, many of these are highly toxic. Diborane, arsine, hydrogen selenide, phosphine are highly toxic. They have an LC50 much less than 200 ppm. So, which metal hydride gas has caused the most fatalities in the last 20 years? Right? These are highly toxic. Yes, sir.
I think you had a slide that said silane.
I'm sorry, what?
You had a previous slide that said silane.
Yes, silane is the gas that has caused the most fatalities in the last 20 years. Why is that? Why silane? It's a pyrophoric gas, right? What's a pyrophoric gas? Pyrophoric gas is what? Something that ignites when it gets released in the air, right? So a lot of people say, well, hey, it's only a pyrophoric gas. We know how to handle that, right? Along with that is silane can be released without immediate ignition. We have been researching silane for 40 years. I'm presenting at a fire and explosion conference next week in Rhode Island. Professor Chen and I have been doing a lot of silane releases in the last 5 years. We've written quite a number of papers. We still don't understand about 5% of its behavior. And we know that we can create conditions in which silane can be released without immediate ignition. We'll talk a little bit more about that later on. I think what you need to be aware of is the other metal hydride gases. They also have secondary or subsidiary hazards. Flammable gas, pyrophoric, right? One of the other things many people forget is when they scrub these metal hydride gases, you'll form hydrogen. And as a result, you have an additional hazard associated with that material, arsine, phosphine. There have been many accidents when researchers have used chemical scrubbers to remove or neutralize the arsine and phosphine, and they generated hydrogen as a byproduct in that chemical neutralization, and they wind up with an explosion in their device. Variety of pressures, but the thing that you need to be aware of, many people think propane is a very flammable gas, but in fact propane has a very narrow flammable range. Look at the flammable range of the metal hydride gases. Diberene, almost the entire concentration range is flammable. So you need to be aware of the flammability hazards associated with these metal hydride gases. What's the definition of pyrophoric gas? What happened here? What do you think happened? This gas cabinet was bolted to the concrete. We were ventilating it at about 150 CFM. Now, what do you think we were doing? Professor and I rigged up a device. We were actually pushing silene into the middle of the gas cabinet through a 1/4-inch tube. We were able to release it without immediate ignition. What now happens? Once it gets into the exhaust or into the cabinet, it mixes with the air, and you have, on a steady state condition, you have a metastable mixture of silane. Now, when does it ignite? 99% of the time, when silene doesn't immediately ignite, it ignites when you shut the flow. That's essentially what happened here. I have other videos in which you'll see us shutting the flow remotely, and when we shut the flow, what happened? Ignition is initiated right at the outlet, and it propagates right through the silane, and it causes the detonation. This gas cabinet exploded from a steady state release of silene into the cabinet, even though it was properly exhausted. We'll take a look at this one more time. So, think about standing in front of that gas cabinet. Now, let me give you another statistic. All 7 fatalities with silane occurred during cylinder change. The worst one I investigated was in India. The window took the guy's head off. The door of the cabinet threw him against the wall. Okay? So, when you're using pyrophoric gases, you need to be aware that you can release those under conditions in which it may not immediately ignite. Now, safety people would say, well, you know, that's a 10 to the minus 6 event, right? 1 in a million. Would you like to win the lottery? Right? So, let's take a quick break. We'll take about 5. I'll entertain any questions anyone might have while we're taking a break, and then we'll reconvene.